Hello, 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 and welcome back to another intro workshop for us here at the Information Security Club. My name is Jeremy Stewart. I'm going to be running the workshop tonight. I'm a director in the club, past president, presenting on binary exploitation, a favorite of mine and a rough one for most beginners, but we're going to go through it together, and hopefully it's going to go all right. Just before we start, some announcements to make for the club. The first is that registration for our Capture the Flag competition, Magpie CTF, will start on November 15th. For premium members, that is if you've paid the club fee and signed up. So those premium members get early access to the CTF. There are a limited number of registrations, and those premium members get first shot to sign up. We'll be making the announcement for when the general public can sign up after that. The other is that we will be doing a workshop. We will be running a workshop with another club on campus called Hackier Learning. It's run by a group of software engineering students, and that's going to be on the 4th of November. That's this Thursday. It's going to be an introduction to common software exploitations and what to look for and how to prevent them. Buffer overflows, the topic we're covering tonight, is going to be one of the topics in that. I've managed to cram it down to about 20 or 25 minutes. It's going to be pretty quick and dirty, but tonight you're going to get the full experience with the full workshop on it. So again, that's it's a workshop with Hackier Learning that's on November 4th, and there's going to be a sign up for that in the club Discord. So with that, I just want to make sure, can someone let me know that I'm coming through loud and clear, no problems? Takes a while for the chat to come back. Meantime, I'll get ready to share my screen. Awesome. All right. Someone's letting me know that, that it's all good. All right, with that, I will start the presentation and share my screen. Screen one, is that screen one? That is screen one. Awesome. Okay, so I've already put it up, but the attendance form for today's workshop is... Sorry about that. The attendance form for today's workshop has been posted in the chat. There's the bit.ly link if you need that. Remember that if you attend at least half of the workshops, that qualifies you to be a voting member of the club. You get to vote in the elections and have a say in how the club is run. So attendance gives you participation in the club. I also welcome to what looks like a bunch of 525 students in the chat. It looks like Dr. Henry has given out participation marks. For, I think, a lot of you, this is going to be a lot of review, but I think you are probably going to find some stuff that you will find helpful. I'm pretty sure you guys are going through assignment 2 right now in 525. I remember what that's like. That's pretty challenging. So I think there might be a few things in here that might help you with that. As well, I posted a link in the chat to download the files for this workshop. The link is there on the screen, so you can download those files and open them up. I've included the source code, the C code, as well as the compiled binaries for you to use for this workshop. This is going to be the first time that we've hosted some of these on our website, which means that you will be able to get rid of that, which means that you will be able to get flags from this workshop. We've never really done it that way. We tried it last year, but we didn't quite figure it out and it wasn't working properly. Where can we find the link for the Hackier Learning seminar? Someone asked. There should be a link going up in the club Discord. I don't think it's posted yet. It should be posted sometime this evening. They just got the poster made. And I believe there's a sign up for it. So look out for that. Otherwise, I'm going to assume that people have signed the attendance form and that people have downloaded the files, and we are going to go. So There we go. So an introduction to binary exploitation, buffer overflows. First, I want to thank Dr. Henry for his assistance with the examples and the slides for this. Again, if you took his Computer Science 525 programming security course, then these slides are going to seem familiar to you. I've directly stolen some of the stuff that he does. I think he does a very good job of teaching it. But when we were starting this club and we needed to start this topic, I went and asked him for help, and he shared the material from his course with me and was very generous in helping us get it started. So he is the basis for a lot of what we're doing in this workshop. But we are also going to learn other things. Question in the chat was, do we need to download the files in Kali or just onto our desktops? It is going to help if you download the files into Kali. They've been compiled in a certain way. They're more likely to run in your Kali VM than they are on your desktop, because it'll depend on what kind of desktop you have. Yes, so thanks to Dr. Henry for this. And another sort of word of warning is that this topic can be really, really overwhelming, especially if you're a first year or a second year computer science student, or if you haven't done any computer science. Which some people in the club, that's the case. This requires a lot of background knowledge. It requires that you know a lot of what's going on underneath the hood of your computer. And I'm going to show you a lot of that. Some of this is going to be simplified. Sometimes I'm not going to give you the full story on what's going on because it just takes too long. This workshop is essentially a week of Dr. Henry's 525 course, compressed down sort of into 2 hours. So if you come out of this feeling like that was a lot and I don't know what's going on, that's okay. That's perfectly fine. You stuck through it. You gave it a try. It's important to just know how these, sort of be exposed to these ideas rather than to have mastered them in 2 hours. Also, it's your first try. You're not expected to be the master of it automatically. For everyone in 525, keep grinding away. This is the sort of stuff that you're getting good at right now and practicing a lot of. So yes, I just want to say it's okay to be overwhelmed. Tell me in the chat if you don't understand something. Ask lots of questions. Ask me to repeat something if you didn't quite get it. By all means, that's what we're here to do. There's no point in sitting here for 2 hours and going on if nobody learns anything. So, the goals of this workshop. So the goals of this workshop are to learn about buffer overflows, recognize vulnerable functions, so things that are vulnerable to the kinds of exploits that we cover in this workshop, and then how to analyze vulnerable programs and look for the vulnerabilities that we're going to learn about. And then we're going to execute some binary exploitation on a few toy programs that I've built. Helpful courses. This is something we do at the beginning of all of our workshops. We like to connect the things that you do in class with the sorts of skills that are going to be helpful to you out in the real world. We like to say that our club connects the stuff that you learn in class with hands-on skills so that you realize that the stuff you're learning in class is actually really useful. You might just not realize it yet. So helpful courses are Computer Science 355, the Computing Machinery course. If you remember ARM assembly, learning it in that course if you took it. That stuff is all really handy for understanding what's going on in binary exploitation. And again, Dr. Henry's Computer Science 525, Principles of Computer Security course. I finished it last year. So I really enjoyed it. It's a challenging course, though, as you in 525 are learning right now with assignment 2, I'm sure. So tools that we're going to use are GDB. This is a debugging tool that's used on the command line for binaries. If you did 355, you've definitely used GDB. The other one is something called Pwn Tools, which I've asked you all to download before the workshop. The instructions for how to install it are in the announcements channel of the club Discord, if you haven't done that yet. But we announce it a week in advance to give people plenty of time. So please, quickly, if you can, go install that. It's going to be great. I'm going to show you how to use it and what it helps you do. So to start out, we need to establish some sort of ground rules, some basics of how things work. And If you did 525 again, this is going to be a repeat, but for everyone else, I'm just going to ask you, what are these? And feel free to toss it into the chat. These shouldn't be foreign to you. In fact, the answer is on screen several times. And I'm sure if the chat could respond right away, I would see plenty of people saying, these are strings. And they certainly are. These are strings. We use them all the time in programs. They look different in different programming languages, but they're pretty common. We see them all the time. Next question is, what is a string? And the answer is, a string is just a sequence of characters. So it's better to think of a string as just a bunch of characters. So this is the string hello world. We see it all the time. It's something that we use in programming. Then the question becomes, what is a character? And you can answer a lot of things. It's a letter. It's something that you can type on your keyboard, but in most languages, it's actually considered just a data type. So characters are representations of letters and numbers and other weird symbols sometimes. And so we can think of a character as just a data type. And luckily for us, in almost every place you're going to look, a character has a size of 1 byte. And that's going to be important a little later on, but it's important to remember that a character is just 1 byte. So, of course, what is a byte then? If we keep going down, the answer is a byte is just 8 bits. This worked a lot better when we were in person, and I've done this 3 times now, but only ever once in person. It's usually is a little bit of back and forth with people to keep them engaged, but unfortunately, we just get to do the camera thing right now. So yeah, a byte is 8 bits, and that is a byte. So those are 8 bits. And then, of course, what is a bit? We're getting really down to the nitty-gritty. And the answer is a binary digit. So just a 1 or a 0. And remember, and I'm going to go over this and talk about this a bunch, this is the language that your computer speaks, the 1s and the 0s. This is what it understands. This is what it works in. And this is why I'm getting right down to what a string is, what a character is, what a byte is, because you need to understand that inside of the machine, it's just 1s and 0s. And we're going to play around with those 1s and 0s. This is why it's called binary exploitation, because we get to mess with the binary in the machine. Somebody asks, what happens when you use non-ASCII characters? Does it get stored internally as multiple characters? It depends on the encoding. There was something in our club Discord recently that dealt with non-ASCII characters that were encoded in a different way. You don't have to know this. But I ran into problems recently trying to do this workshop, actually. I was trying to write an exploit to demo for you guys, and the answer kept coming out wrong. I'll come back to that a little later. But yes, the answer is it can get stored internally as multiple characters. So 1s and 0s. So then what is a string? And we said that the answer was a sequence of characters, but we know what a character is. We know that a character is just a byte, so we can say that a string is also an array of characters. So if you were to store characters to look like a string, they might look like this. You'd store them in an array. And then we know that the characters are just bytes. Sorry, I forgot about this. I forgot to mention this. We're going to be using the C programming language. And in the C programming language, and this is very important, a string is null terminated. You're going to hear people say that a lot in your life, probably. But a string in the C programming language is null terminated. And that means that at the end of the string, there is always this null character. Let me see. I believe, yes, there's my laser pointer. There is always a null character, and this right here represents a null character. It just means like a 0 character. Whenever C is reading through a string or an array of characters, whenever it hits this, the null character, it knows that that's the end of the string. That's what it remembers. So it's very important in C that you have those at the end of your strings. C will sometimes put them in for you if you forget them, but they're always there in the background if you don't see them in C. So this tells you that this is the end of this string. So a string is an array of characters, and it ends with a null character. And then what I was trying to get to earlier, an array of characters is also just an array of bytes. And when we represent characters as bytes, we can represent them in many different formats. So this is something you might have seen before. This is called an Ascii table. And this tells us and tells the computer how to encode different characters inside the computer in different formats and what they look like. So for example, the character a capital A up here, these are different ways of encoding it. So there's decimal. In decimal, it's the number 65. In hexadecimal, it's 41. In octal, 101. And in HTML, the A character can be encoded as this right here. So the computer can see the character A in different ways. But this is important for us because this is how the computer stores these things. Let me just turn my light on as it's getting dark outside. This is how the computer stores information. So we're going to see how it does this. We're going to go a little more in depth about this Ascii table. So the character A in Ascii, this is it here. If it was in hexadecimal, this is what it would look like. So it would look like 41. If you did Computer Science 329, Intro to Information Security, there's a whole worksheet that you have to do on hexadecimal and binary and characters. We're going to do it very quickly. So hexadecimal is just a way of encoding numbers and information. So this 0x at the beginning here tells you that this is a hexadecimal encoding. All hex codes usually will begin with 0x to tell you that everything after it is hexadecimal. And we can see here that the A is encoded as 41 in hexadecimal. And then in binary, this hexadecimal can be translated into this, 0100, 0001. And indeed, that's what the computer stores it as. So the computer is going to store it as this right here inside. Remember, it just speaks in zeros and ones. Everything is just on or off, or 0 or 1. And so this is a chart down here that converts between numbers, and then their binary representations, and then their hexadecimal representations. I'm not going to go over how to read binary if you don't know. It's interesting, and you're going to have to do it for Computer Science 329 and for Computer Science 355. This is all important stuff to know. But this is what the translations are right now. So if I had to translate A in hexadecimal is 41. So the first 4, 0, 1, 0, 0, that matches what we have here. The 1, 0, 0, 0, 1 matches what we have here. So this is 4, 1 in hexadecimal. And if you put all this number together in binary, if you just read this all as a binary number, it would be the number 65. That's why the decimal here is 65. So this is a lot. You don't need to memorize this for this workshop. I'm just telling you this because you need to know that the binary stuff in memory can be translated into other forms. And so if I ask you, what is this? I'm going to give you 2 minutes. What is this? This is binary, and what does it translate to? Actually, I'll give you about 1 minute. Someone has what I think might be the best answer, which is translate to in what? And that's the point of this question. So you could look at this, 0101, find it on the table down here. 0101 is 5. 1010 is A. 5A on our table in hex is Z. So this could be a Z. But it could also be 90, as we saw before. If we just translated this into a number, it's 90. And of course, if we translate it into hex, it's 5A, as we just saw. So the point of this is that if I ask you just to translate some binary, it could be, it depends on what you're interpreting it as. And the computer does this too. The computer is just going to store, remember, ones and zeros in memory. And when you ask it to read that memory, you usually have to tell it what you're reading the memory as or what you're interpreting it as. So this could be the letter Z, could be the number 90, or it could be in hex 5A. And so in ASCII, the string hello gets translated into hex and it looks like this. And then in binary, it looks like this. And the reason I'm showing you this is because the binary is really long. As you can see, this is getting really big. We don't usually represent things in memory as binary. We usually represent it as hexadecimal, as this right here. It's shorter, it's easier to read, although you can't just read that off straight unless you've memorized and can speak hexadecimal. Read or write hexadecimal, which would be really impressive if you could. And somebody points out, yeah, no null byte. That's right. Remember, there's got to be a null byte if it's in C. There should be a 00 at the end of that. But yeah, this is what the string looks like. Hello. This is what it looks like in hex. This is what it looks like in binary. We just use the hex. So in this workshop, we're going to use a lot of hex. And I did all of this just to show you that the hex represents some binary, but we read it like this for the sake of convenience. So we're going to go back to our string, and we said that a string is an array of bytes. So we've got our array of characters. These characters are bytes. Let's represent them as hexadecimal, and we go through and we convert each character into hexadecimal. And that's what hello world is going to turn into in hexadecimal. And then again, to show you how clumsy it is, this is what it would look like if it were in binary. But screens aren't big enough to hold long strings in binary, and it's just inconvenient. So again, we usually just use the hex. And we're going to see later on in this workshop that your computer is going to represent the internal memory in hex as well. So the things I want you to take away from this: 1, a string is an array of bytes. 2, it is terminated by a null character. And 3, we usually represent that in hexadecimal. We usually look at it and talk about it in hexadecimal. So you're going to see lots of hexadecimal tonight. So going on into part 2, having established all those ground rules, what is a buffer? So this is called, there's this exploit called a buffer overflow, and the question is, what is the buffer? And the answer is, it's a temporary place to store data, usually from input, and it is very common in C and C++. So we're going to show you an example here. This program is called Buffer Zero. This is included in the files that you have. So if you're not familiar with a C program, this is what a C program looks like. This is what we're going to be working in completely. This is called the main function. This is where the program always starts, int main. Inside of here is this is an array. So these brackets mean there's an array. Its size is 44. So there's space for 44 things in this array. What things does it hold? Well, that's declared right here. They're characters. And its name is buffer. So this is not, you don't have to call it buffer. You could call it whatever you want. I just call it buffer to make it obvious. But this is an array of characters of size 44. And so it's going to hold characters. This is how you hold strings in C. The program then prints out, printf prints, enter your name. It then runs gets buffer, and it then prints you entered a string. It prints out a string, and the string it's going to print is whatever's in the buffer. So it gets is going to take some input from you and store it in the buffer, and then it's going to print it out for you. Return 0 then finishes the program off, and it ends. So you can go ahead and run this. If you downloaded these files, let me find my terminal. And I was practicing before. Here's all of the files that I gave you. This one, remember, is buffer 0. If you can't run it, it's because you might have to run chmod on it. So once you unzip the files, you have to run chmod plus x buffer 0. And this will give you execution privilege on the program. Kali, I believe, will not let you run this straight from unzipping it as a sort of protection or precaution. You have to tell it, I want to be able to run it, and that's how you do it. That's chmod plus x, and then the file name. So go ahead and run buffer 0 by typing. Actually, this is probably a little small. Make this bigger. There we go. Go ahead and run it by typing // and then the program name, buffer 0. And this is how you run a binary in your terminal. And as predicted, it says enter your name. My name is Jeremy. And then it prints it out. And so that's what the buffer does. The buffer just held the program in memory for us so that we could use it later. That's it. That's the basics of what a buffer is. But there's more complicated things to it. So here's another program. It's called buffer1. It does almost exactly the same thing. There's just one difference. It uses scanf. Scanf takes something that you enter, a string, and puts it into the buffer. So let's go ahead and run the scanf. So that's going to be buffer1. Just enter your name, Jeremy, and it prints out Jeremy. So you're saying, why are you doing this to me? This is the exact same program. Why would you just write the same program with two functions? Well, there is a difference between these two programs. I'm going to give you about a minute and a half. I'll give you between a minute or two. We'll see how the answers come in. I want you to tell me what the difference is between these two programs. I know that the difference is that one uses gets and one uses scanf. I want to know what the difference between gets and scanf is. See if you can do it by running them. Maybe run some research, whatever you need to do to figure out the answer. I'll give you about a minute. If anyone's having any problems, toss it in chat. All right, I'll stop the time there. We've got two guesses up. The first guess that I saw was does not check for the length in the second. Not quite. It's close to that idea, but the answer actually came up and it's scanf stops after a space. Yep, and someone else just tossed it in. Scanf stops after it finds white space. You might have seen me playing around here, and that's in fact the difference. So if I type my name in the first one, Jeremy Stewart, it prints it out, whereas the second one that uses scanf only tells me that my name is Jeremy. It drops the Stewart at the end. And there's a reason for this, and the reason is that these are two things that do pretty much the same thing. Scanf and gets do pretty much the same thing, but they are slightly different. And because this is an intro workshop, we're going to assume that you're not familiar with this or how to find it. So you could have Googled this, you could have played around with the programs to find out manually. I'm going to show you a quick way to find out what functions do, and that's the manual page for it. So if you installed, or in Kali you should have it, the C programming language, you will also have a manual for all of the functions in C. So what you type is man and then the function name, so gets. And here is, make this bigger, here's the Linux Programmer's Manual page for the gets function. And it just tells you that gets a string from standard input. We're going to come back to this in a while. Notice here that it's in its description, it just says never use this function. There's a reason that we're using it in a workshop on vulnerabilities. So it'll tell you what it does. And it'll tell you when it stops. So it says it reads a line from std in, which is your command line, into the buffer pointed to by s until either a terminating new line or end of file, which it replaces with a null byte. Our friend the null byte shows up again. So that's what gets does. We'll press Q to get out of that. And then we'll type man scanf. And here's the manual page for scanf. It's much bigger. These can be pretty intimidating, but they're important to get used to if you ever do any C programming. The description here tells you all about what scanf does, and I should have looked at it beforehand. It's not showing up obviously here to me. Nope, here it is. It's up. Oh, nope, that's gets again. Somewhere around here, it tells you that it reads this until it finds a new line or an end of file or a white space. And I'm not going to go through. We're just going to keep going. But those manual pages are important. You need to look at those if you're trying to analyze a program to figure out what it is that they do. And just a moment. My Discord is going nuts, and I'm going to silence it so we're not bothered anymore. So that's the difference between scanf and gets. Remember, those man pages are important. If you were trying to figure out where the problems are in this program, those manual pages can help you. So like we said, gets reads until it finds a new line, an end of file, whereas scanf goes new line, end of file, or a white space, which is why when I put a space in my name, it only read the first name off. So there is a program. This is the gets program. So there is a flag up for grabs here. You can get a flag out of this, not if you're running it on your local machine, only if you connect to the version of it that we have running online. And to connect to it, you're going to use something called Netcat. The command is nc. Then you're going to put a space and the address, the IP address of the machine that you're connecting to, and then the port number. That's what this is. This is going to connect to a machine that we have set up on the internet ourselves, and it's going to run this program, and you need to try to get the flag out of it. You can get the flag by crashing the program. And I'm going to remind you that this is a buffer overflow. So let me just put this command in here. 754. So there you go. I'm going to give you about a minute to play around with it. Remember, buffer overflow. See if you can get the flag. Got one person that has it. All right, I'm going to call that time. So the question is, how do we get the flag out of this? This is actually pretty much a challenge that we had in our CTF last year. It was the easiest of the binary exploitation problems. We were super disappointed because the solve rate on it was really, really low. And I felt especially that might have been my fault because I didn't teach this well enough. So we're doing that problem in this workshop now. How do we solve this? Well, remember it's called a buffer overflow. Here's the buffer. It holds 44 characters. This program is asking for your name. It's giving you 44 space for 44 characters. It's assuming that your name must be around 44 characters. But in binary exploitation, the thing that we always want to start out with is figuring out how to crash the program. If we can crash the program and get a certain error message, then we know that the program is going to be vulnerable to binary exploitation. And the way that we do that is, and this is a running joke in our club, you try screaming at the program. So we're just going to yell at the program, we're going to fill it with a bunch of A's. Remember that gets function, and that's what's running under the hood. That gets function is just going to take what it finds until it gets to a new line or until we hit enter. So we're going to say that this is our name. And the program says your name is this. That might seem weird. Remember, it's only got space for 44 characters. This is way more than 44 characters, but it memorized our whole name. And then we get the flag out at the end. So again, the first thing you should do is scream at the program. And you can't see it here. It doesn't print it out. But what's happened is there should be a message after this telling you there's been a segmentation fault in the program. So that's buffer 0. You've overflowed the buffer, and this one spat out a flag for you, but that's not going to happen on all the programs out there. In fact, if I go back, let me just demo for you. We're going to run buffer 0, which is the one that used gets, and we're going to do the same thing. We're just going to scream at the program, see if we can't make it crash. And there it is. Tells us what our name is, and then the program says segmentation fault. That was happening up here for the one you were connecting to online, but it wasn't sending you that message over your connection, over your Netcat connection. So we're going to look more into this and what's going on there. So what's the problem with these things? And the problem with gets and scanf and other functions as well is that they don't do something called bound checking. So they don't check the limits of what it is that they're supposed to be putting in. They don't check the limits of the buffer that they're putting the input into. So Java and Python, if you tried to do things like this, would throw exceptions. They would not let you do it. Python is programmed to extend the size of the array that you're putting it in to hold the amount of stuff that you're typing in most of the time. But they're much more forgiving, or they stop you. C doesn't do that. It's because C is an older programming language where you had to manipulate and control the memory in the computer. We're going to see what that looks like. But you would control that memory in the computer, and C assumes that you know what you're doing when you're programming and you know how to control that memory. And if you don't control it properly, these kinds of things can happen. So C and C++ do not check those things. And they don't even notice. They just run the program the way that you tell it to, and nasty things are actually happening in the memory underneath the hood in these programs, which we're going to see in a little while. But they just run it. They just assume you know what you're doing. So what? So why do we care about all of this? The answer is that scanf and gets and then other functions are big problems. The programmers, we're going to look at the programmer's manual for gets and the programmer's manual for string copy to see what it says about them. And then we're going to see what compiling programs with the gets function looks like. If you look in the manual for gets, which we looked at before, there's a section called bugs. Remember how before it said never use this function? Well, if you scroll down, there's a section called bugs. And this entry is just, I think, pretty funny. It says never use gets. The manual for this function just tells you never to use it. Because it is impossible to tell without knowing the data in advance how many characters gets will read, and because gets will continue to store characters past the end of the buffer. It is extremely dangerous to use. It has been used to break computer security. Use fgets instead. So fgets is a better version of gets that will check the size of the buffer. But the phrase "it is used to break computer security" is pretty ominous. And then next, string copy, which I think might be my favorite entry in any of the manuals. Remember, these are like technical manuals. They're supposed to explain how to use things. It says, if the destination string of a string copy just copies one string onto another, is not large enough, then anything might happen. Overflowing fixed length string buffers is a favorite cracker technique for taking complete control of the machine. Anytime a program reads or copies data into a buffer, the program first needs to check that there is enough space. This may be unnecessary if you can show that overflow is impossible, but be careful. Programs can change over time in ways that make the impossible possible. In ways that make the impossible possible sounds like something a wizard tells you before you go on a quest. It's a weird thing to write in a manual, but basically this is just warning you that dangerous things can happen if you use string copy. My other favorite thing is that when you compile a program that's using gets, so that program I showed you before, the one that we ran, when I compiled it, my compiler actually warns me and says, hey, you're using gets. That's just really bad and you shouldn't be doing it. You see right here, warning, the gets function is dangerous and should not be used. The compiler I have will compile it. I've heard of compilers out there that just refuse to compile programs that have gets. They just say, look, this is dangerous, you shouldn't do it. I'm not going to be a part of it and I'm not letting you do it. Thankfully, we've got one that lets us, it just warns us in advance that this is really dangerous. You shouldn't be using gets. Now, the other thing that is such a problem, or the other reason that this is such a problem, is that here is a chart. This is a survey. It's called the Common Weaknesses and Exploitations Top 25. So this is the top 25 sort of security or software security bugs or hacking techniques that exist out there. And as you can see, there are things on here like integer overflow, out of bounds read, out of bounds write, or improper restrictions of operations within the bounds of a memory buffer. This is really high up on the list. This thing that involves the memory buffer, this is buffer overflows. And you can see the score here of 75 is almost double what the next score is. But all of these things are in the family of binary exploitation. This was 2019. If we go to 2021, it was redone this year. It's switched around a little bit, but this is still number one on the. It still has the number one spot on the list. Out of bounds right. They changed how they calculated this a little bit. So here's something that exists out here telling you that this buffer overflow, this binary exploitation thing, is still one of the biggest deals out there. The other problem is that C is a really popular programming language. And so this is a video that was put together showing the sort of popularity of programming languages over time. This is 1975. As you can see, the C language is down here. It's just come onto the scene. Fortran and COBOL are the most popular programming languages in the world. Now, they're sort of things that you use to age somebody if they ever say that they used COBOL or Fortran. But 1975, C is just starting to be an up-and-coming language. By 1980, we can see that C is halfway up in popularity. It's about to overtake COBOL. C++ has also just come on the scene. C++ can also be vulnerable to these kinds of binary exploitation and buffer overflows. By 1985, C is almost at the #1 place. C++ is coming up. By 1990, C is the most popular programming language and has been for a year or two at this point, I believe. And C++ is on the board as well at #4. In 1993, C is at its most popular compared to other languages. So as you can see, the next most popular language is C++. C is over three times more popular than the next languages down. But the C languages have almost total domination over programming in the mid-90s. And this is year on year. So every year, more programs are being written in C than the other languages almost combined. So it's really popular, and there's a lot of C code being written. 95, C and C++, still crazy popular. Java and JavaScript are coming up. By 2000, C is still the most popular, but Java is #2. JavaScript, PHP are both up there. The internet's starting to become a big deal, but C and C# are still on the list. 2005, Java is winning, but C, C++, and C# are still in the top 5. By 2015, they're falling down, but they're still up there. And to finish, I had to finish in 2019. Python overtakes JavaScript and Java because it's just a nice language. So this is just to show you that C has been popular for a very long time, and for a long time just dominated in programming languages. So there's tons of code that already exists out there that for years was all being written in C. And C and C++ are systems languages, so they're very popular for writing things like Windows, Linux, and OS X. Those are all written using C and C++. iOS and Android are all written in these languages. Databases systems like Oracle and MySQL use it. Vehicle electronic systems. So if your car uses any computers to control its brakes, it's very likely that it's using C somewhere. Airplanes use C in their programming pretty frequently, and it's just everywhere. So C is vulnerable to this buffer overflow thing, and it's used in all kinds of scary places. And you might be sitting there going, oh my God, if this is all out there, what are we going to do? Why aren't planes falling out of the sky? And the answer is that I had to do a lot of tricky things, as you saw, to make this exploit work. Remember the compiler warning us about it? Well, there's all kinds of safeguards to prevent its use. If you take Computer Science 525, you will learn more about those safeguards. Someone in the chat mentioned stack canaries. That's one of the safeguards. But these things, this buffer overflow thing is not common anymore because there are lots of protections against it. That being said, it still happens a lot. I searched in the news just the other day. There were like 6 or 7 different articles about companies having to patch their software because of buffer overflows that were found from companies like Google and Apple. It's still really important. It still happens all the time. So we are going to look at why the seg fault is such a big issue. Why are they on top of that list of vulnerabilities? If the program just crashes, how can that be hacked? That's the big one. We don't only want to crash these programs, we want to figure out how to exploit them. And to understand that, we need to understand how the stack works. How are we doing for time? About 50 minutes. So again, this is an intro workshop. We're going to assume that you probably haven't taken a lot of computer science. So a stack is a data structure that we use in computer science quite a bit. And we equate it to just a stack of plates. The idea and the phrase you will hear with them is last in, first out. What this means is that the last thing that is put on the stack is the first thing to be taken off. And this diagram here shows you how that works. So this box with the 1 in it, this is the stack. To put something on the stack, we say that you push it onto the stack. So the 2 gets pushed on, then the 3 gets pushed on, the 4, the 5, and the 6. And you can see, like the stack of plates, these values just start stacking up. The problem is, if I want to take, say, the 2 out of the stack, I need to take everything off before the 2 to pull the 2 out. So like a stack of plates, to get something further down, you have to pick up and move everything off of there. And this is an important concept to understand because in the memory of the computer, it works like this as well. There's an area in the memory of your computer called the stack. And it works like this. It puts things on top and then takes things off as it goes back. And to understand that, we need to understand RAM, or random access memory. Remember, you've got 2 parts in your computer, the hard drive and the RAM. They're both kinds of memory. The big difference is that when you shut your computer off, the stuff in the hard drive will stay there, whereas the stuff in the RAM will not. And the stuff in the RAM, and there's a lot of stuff that's in there, is really important. Your computer uses it for functioning sort of minute to minute. If you copy something to your clipboard, that gets stored in RAM. If you're opening websites in a browser, all of the stuff on that website, that gets stored in RAM. It's sort of the short-term memory of the computer. Someone once in our club said it's like a scratch pad. If your computer just wants to jot down some notes that it needs for a short amount of time, or it just needs quickly, it uses and puts it into RAM. Not that one, this one. So this is how we represent RAM when we're trying to do binary exploitation. It's separated into different areas. So it's usually represented as sort of a big, tall, long rectangle, and it's divided up into different areas. The area that we're interested in is located in the high area of memory. It's called the high area because the memory has addresses. The same way that houses on a street will have addresses, the RAM has addresses for each slot of memory that it has. And they go from low addresses all the way up to high addresses. These might look like weird addresses because they have letters in them, but that's because they're using hexadecimal. Our friend hexadecimal. This is partly why I wanted to show you hexadecimal before if you weren't used to it. Hexadecimal is going to be all over this workshop. So the memory addresses are done in hexadecimal. The stack, again, lives at what's called the high area of memory because the addresses are bigger. They're the higher up addresses. The lower area of memory down here is an area called the text section. There's also an area called the heap. It's sort of used in conjunction with the stack. We're not going to deal with these. There are exploits for both of these areas of memory. If you want to go further into binary exploitation, you'll learn how to do heap overflows. But we're going to stick with buffer overflows, and those are going to exist down here in the stack. So our diagrams are going to look like this. This is going to be the RAM, the memory. It's going to look like sort of a bunch of cells in an Excel spreadsheet. And it can be a little confusing, but here's the low memory. It's down here. This is an address in hex. It starts at 0. And then up here, the high address, I just put all Fs. But this is the high area of memory. The amount of stuff that is held in each one of these can be 4 or 8 bytes. I believe, yeah, we're going to use 4 bytes for this. So each one of these each one of these boxes can hold 4 bytes. They're like shelves on a bookshelf sort of thing, and each one of them holds 4. If it was 4 bytes, that's the same as 4 characters, and that's going to make it easier for us to sort of understand and fill in this diagram. An important thing to understand is that memory writes one way and the stack grows the other way. So let's pretend that we have some code down here. And it might be a little difficult to read. What you have is a main function down here, and then function 1, function 2, and function 3. The main function calls function 1 calls function 2 calls function 3. And the way that this works in your memory is that each time a new function is called, it gets a new chunk of memory in the stack. So let's say that the main code called function 1 then gets some memory in the stack. Function 1 then calls function 2, so then function 2 gets some memory in the stack. And important to note that the stack is going to grow down this way. It starts off at the high memory, it starts off at the very highest addresses, and then it goes down towards the low memory addresses. And then function 2 calls function 3, so function 3 gets a chunk of memory in the stack in your RAM. And then when function 3 is done, when it's finished, it then goes back to execute code in function 2. So what would happen is that would then disappear. In order to go back in the stack, remember it's like a stack of plates, we need to remove the last thing that was added. And so they get added when they call each other, and then when they go back to the previous function, they get rid of the memory that they store for themselves. So these things are called stack frames. These pieces of memory, each function gets its own stack frame because it takes a piece of memory in the stack. So that's important to remember. And then the way that this works, the way that it's able to go from one function down to the other and then back is that it keeps something called a return address. So when function 3 is created, it remembers the address that it came from in function 2. It remembers the memory address. Remember, there's memory addresses for each of these slots. It holds the memory address for function 2 that it goes back to when it's done running when it's done running. So when function 3 is finished, it's going to go inside of its own scratch pad here. It's in the stack. It's going to say, what address do I go back to for function 2? I remembered it, it's right here, and it goes here. When function 2 is done, it does the same thing. It says, where's that return address for function 1? It's right here. It's always in the same place in the stack frame, in that chunk of memory for the function. So it knows I go back to function 1 by going to this address. This is going to be very important. We're going to see this more soon. So here's a program. I've called it Overflow Zero. This is a pretty silly Sorry, I've been ignoring the comments. Here's a funny comment. On my machine, when I try to run buffer zero, I get a message warning this program uses gets, which is unsafe. That's nice. I like that. I like that you get that message. Somebody also asked, I don't see the attendance link on the InfoSec Discord. Someone might have posted it already, but I had it at the beginning of the workshop as well. It might be further up in the chat if you can see it. If not, if someone could post that for Boots. Okay, so we've got this program. What does this program do? Well, we see here there's letters. It's an array of characters. It's called letters. So this is, again, this is just a buffer. It's named something different, but it's just a buffer. We then declare an integer, I, and then we run a for loop. And if you're not familiar with C or Java, this is what a for loop looks like. If you've only done Python, this is going to look a little different. But this is the for loop. It says start at 0, go until it's 128, and increase the size once every time. And all it's doing is saying that letters at I is equal to A. So this is going to run a loop 128 times, and it's going to put 128 A's into this letters array. Then it calls this function, pour it on doc, which is a reference to a song I was listening to when I wrote this. What does this function do? Well, it passes this array, letters, this thing right here, passes it to the function. So this function gets a string of characters just called string. So letters here is just going to be called string up here. So this is the letters array with 128 A's in it. It declares another array, this buffer, it holds 4 characters, then it runs string copy. And it's going to copy the string into the buffer. And we know, we've seen what happens when you try to do this. String copy is dangerous. String copy does not care what size the buffer is. String copy just says, I copy everything from this thing into this thing. And if you run this, you'll get a seg fault in your machine. Just a second. What was the name of that one again? Overflow Zero. Yep. Overflow Zero just produces a seg fault, just like we want. So let's take a look at really what's happening. And this is where we're going to start really understanding where buffer overflows happen and why they're dangerous. So the program starts out, it takes this character array is going to be held in the stack. It's a big chunk of memory, so I'm not going to be able to show you the whole thing. Let's just assume that it goes way higher up here. And I've shown you here, this is the main stack frame. Main is a function in a program, so it gets its own stack frame in stack memory. But in there, should be, yes, okay. So there's a bunch of letters, and it starts writing the A. So this is the area that the letters are going to go in. It just starts copying those A's in. Remember, we're going to represent them in hex. And A, the character A in hexadecimal is just 6-1. You're going to probably know that quite well by the end of this workshop. When you scream at your program with capital A's, it's just 6-1. Sorry, I think it's 6-1 or 4-1. Anyway, the point is that we're copying A's into the memory. So it copies, and it fills it full of A's. And that's going to go all the way to the top of that stack frame. It's going to be somewhere off my screen because there's way too many A's to put in. So then the function calls, so then main calls pour it on doc, and pour it on doc gets its own stack frame because it's a new function. There we have a new function. So we have a new function, we have a new stack frame. In that stack frame, remember, it's going to hold the return address to go back to main, the main function when it's finished with this to get back. It also has this thing called the frame pointer, which we don't really care about right now, but can also be used to do tricky things. Every stack frame is going to have a frame pointer, and that's going to be important later for trying to figure out how to do bad things. But pour it on doc also has the buffer. The buffer can hold 4 characters, so it only has to take one of these. Remember, each one of these will hold four characters. But then string copy starts. String copy puts 4 characters into the buffer, but it doesn't stop there. Remember, it doesn't care how big the buffer is. It keeps writing. So then the frame pointer changes. Then the return address changes to all all A's or just 616161, and then it just keeps going. So it's going to start writing these A's into the stack frame of the main function, and it's going to keep going and write 128 of them back up into the stack frame. And then when the program is, so then when this function is done, when it's finished copying all of these and it wants to return back to main, remember, it's going to look at the return address in memory that it remembered. Except that the return address is not where it said it was. The return address is not the address to main. It's just a bunch of A's now. But it looks at this and says, that's an address to something in memory. Let's go there. And what happens when it goes to that address, when it tries to jump back to the main function? It calls jump, and then bad things are going to happen. In fact, if we let the program do this, this might be the likely outcome. What your computer does is it keeps very careful track of where it is in memory and where it's supposed to be in memory. That return address, that tells it to keep running the program normally, go back to this address. It would say go back to this address. Sorry, I was just looking at the chat. Yes, sorry, somebody posted a flag in chat. Try not to post it in chat. Post it to our bot, Orchid, in our Discord. Private DM the flag to the bot, sorry. So yes, sorry, going back, if the program was allowed to jump to that memory address that was just all A's, that would be somewhere random in the memory. There could be anything there. There might not be anything there. The point is that the program would be in the wrong place, and it might just start executing the wrong instructions. And when your computer gets confused and can't recover, this is what happens, the blue screen of death, the famous blue screen of death. Luckily for us, there's some protection against this. The computer knows where in memory it should and should not be. So that return address, the normal return address, the computer knows that that's an area in memory that it's allowed to be in. And then it puts certain areas out of bounds and off limits. And so when we filled it with A's, all of those A's, if they're a place that's out of bounds to the memory, instead of the computer getting confused and crashing to try to save itself, it instead prints out the segmentation fault. And the segmentation fault, the core of what this is, the segmentation fault is your computer trying to access memory, the program trying to access memory in a place that it's not supposed to be. And your computer just goes, hey, you're not supposed to be here. If you keep following or if you keep going to this area in memory, bad things are probably going to happen. I'm just going to crash this whole program and save the computer from any sort of failure or bug. So that's what the seg fault is. The seg fault is the return address is probably messed up and the program is trying to go somewhere in memory that it's not allowed to go. And the computer is saving itself by crashing the program, and it says seg fault. It's not very descriptive, but whenever you get a segmentation fault, it's your computer trying to access memory in a place it's not supposed to be. If you haven't done Computer Science 355, these are going to be the bane of your existence when you're writing assembly programs because you have to keep track of the memory. And when you mess this stuff up, you're going to get seg faults all the time. And that means you've messed up the memory in your program. So that's what a seg fault is. It's important to understand. So now we're going to start with the hands-on stuff. Yes, I just noticed someone saying that there was no GDB. They just got the flag by tossing in a bunch of A's. And that's normal. That's the early programs. We're going to start getting into the difficult ones. So this is a program called Overflow 1. There's a flag involved in this one. You have it on your computer as well. If you run it on your computer, it should spit out a message that the flag isn't available. So we're going to run Overflow 1. It just says my password's incorrect, but there should be, overflow1.c. So if I cat that, overflow1.c to print out the program, here's the program. And you're going to notice that down here, so it's going to verify the password. And if the password is right, then it goes and prints the flag out for you. If you're just running this program locally, it'll say flag file missing. So it tries to open the flag.txt file, and if it's not there, it tells you that the flag is missing. So if you run this on your local machine, and this is very common for binary problems, if you run it on your local machine and there's no flag.txt file, the message you will get back is flag file missing. But that's a good thing if you run it on your machine. That means it tried to print the flag out for you and there just wasn't one. So you can work on this you can work on these on your local computer, and then if you get this message, flag file missing, it means whatever you did, it worked. It's just the flag isn't on your machine. In fact, we use this Netcat thing so that we can hide the flag on a remote computer. So you can, this is common again for buffer binary exploit challenges. You'll get either the binary, or if they're nice to you, they'll give you the C file like this, so you can read it. And you get to read it and analyze it and play around with it and try to break it. And when you do, then however you broke it, you upload that onto, or you run it on the machine, the remote machine, and then that spits out the flag for you. Yes, someone in here said, just create your own flag.txt file and problem solved. So you can do that. You can create a flag.txt file on your machine, and then when it prints out that, then you know that it worked. But here is Overflow 1. I'm going to go through a little bit of what this does. You can get started on this if you'd like. This looks pretty complicated, but it's not. It's just doing some fancy stuff. So here's the main function. The main function says if verify password. So this is actually going to call the verify password function. So verify password, it jumps up, the program's going to jump up here. There is then some integer R, a character array, size 16, that holds a password, character array called buffer that's size 16. It then calls this rand string. It passes the password, size of password. So that's this thing up here. This is not where the exploit is. All this is doing is assigning 16 random characters to the password. So it starts off, it gives some memory space for the password integer and the buffer, and then it just makes a random password. The program then says, please enter your password, and you enter your password. And then it compares your password, and it compares what you entered and the password. And if they're the same, it'll print the flag out for you. And if they're different, it'll tell you that you have the incorrect password and your login attempt is reported to the administrator. So I'm going to give you about let's say about 4 minutes, and I'll check in again to see how it's going. Knowing what we know about buffer overflows, see if you can get the password, if you can guess the password or get the password and get the flag out. Again, toss any questions in chat if you're confused, if you're falling behind. If you want me to repeat something, by all means. Sorry, somebody posted, I found the flag, but I don't know how to submit. Yeah, okay. I think you mean submit the flag to Discord. Let me show you. Actually, let me just make sure that I don't have anything that you're not allowed to see. The way that you submit a flag is by, in the general chat? Yes. This is Discord. I assume that you have this. The way that you submit your flag is there's a bot on our server. It is called Orchid. Orchid can be found up here in the Orchid channel. Orchid is also a chatbot. If you talk to Orchid, Orchid will talk back to you. You just have to use Orchid's name. But to send Orchid a message, you right-click and then message. This brings you to your chat with Orchid. And I'm just going to clear the screen there. And then you would just send Orchid the flag. Is not a flag, and Orchid, if this is a flag, Orchid will give you points for it. Otherwise, Orchid probably won't say anything. Oh, Orchid loves hiking. That's great. But yes, if you're new to this, we use flags. This is the way that capture the flag competitions work, is you exploit programs. And someone's saying, I found the flag, but Orchid doesn't respond. Interesting. Let me move this over and make sure that Orchid has this flag, which might not be the case. So just a moment, I'm going to, okay, yeah, multiple people are having this issue. It's possible the flag might be missing. I thought I added them all, but let me just stop sharing my screen for a second and go fix this problem. Yeah, Orchid accepted the flag from me, so let me solve the problem and see if I get the same thing. That looks like the right flag. And Orchid is responding to me normally. Orchid might not be recognizing this flag for some reason. Just test if it's recognizing other ones. Yeah, It's not recognizing this flag for some reason. Let me try re-adding it. There might be some character that it's messed up with. Sorry about this, guys. Okay, it just worked for me. Okay, so yeah, it should be working again. Let me know if people are still getting that problem. Somebody has a question. By all means, ask the question. I don't understand that question. So I'm just going to keep going. All right, I'm going to say that's enough time. We're going to keep going and look at how to solve this in case you didn't get it. So this diagram that I'm using, that I keep using, is a good way to demonstrate how this works. But I promise you, I use this when I am working on binary exploitation problems. In fact, that whiteboard there behind me, whenever I'm working on one of these problems, it has a big old diagram with all kinds of little slots and arrows pointing all around. And that's how I work on these. I draw this thing out myself so I know where everything is all the time. So we start out in the main function. The main function is just going to have a return address and the frame pointer. It doesn't need any memory to hold anything. So it's going to call verify password. Verify password then runs, and it reserves a chunk of memory. And the first thing it tosses in is the return address to main and its frame pointer. So these are going to be two memory addresses. We don't really know or care what they are for this one. So inside of there is going to go the int r. There's going to be space for that password, and then there's space for the buffer. Remember, this is in the stack memory. It's then going to call the rand string function. So there's another stack frame that gets put in here for the random string. It gets a return address to go back to verify password, to go back here when it's done. We don't really care what that does. We know that it just assigns some random password. So we're going to represent that as some random hex values. Then it prints out, enter your password, and then it calls gets. And remember, gets doesn't care the size of the buffer. And so if we just put in 16 characters like this, this is what it would look like in the memory. These hex values are 1, 2, 3, 4, 5, 6, 7, 8, 9, and then again 1 to 7. And so when it made the comparison, it would compare our password to this random password. There is an extremely small chance that they could match because the password is random. It is extremely unlikely, though. If that happened to you, congratulations. That's like winning the lottery. You should have bought a ticket otherwise. But let's just be a little bit clever and remember that we can write past the buffer in memory. What if we doubled up the password that we typed in? Well, if we did that, then it would write the first half of this into the buffer, and then it would keep writing, and it's going to write the same 16 characters, the same 16 bytes, into the password field. And then, when it runs the comparison in the next go, it's going to find that they match, and that's how you hack the program. And I'm just going to show you what that looks like on my computer here. So let's connect to that one. It wants us to enter a password. So I showed you how to do it by typing numbers. If we wanted to break the program like we normally do, we would do the usual thing of just screaming at it. Remember, this is how we try to figure out if there's some sort of problem. If we did that, it would just hang like this if we connected. This is because it seg faults and then doesn't disconnect us. And I hit enter again, and it prints us nothing. If I just printed a certain number of A's, we get the flag. We get the flag because that has written all A's into the buffer and then copied over the password with all A's. And remember, the key to this is that I want it to be able to finish running the program. If I just write too many A's, it's going to write over the return address, and the program's going to crash without printing out our flag. And somebody says, and they ask correctly, couldn't this be avoided if the password was initialized after the buffer? Yes, it could. If the password was down here and the buffer was up here instead, then you wouldn't be able to write over the password field. So if buffer and password right here were switched, it was buffer and then password, then this wouldn't be possible in the way that we have it. The buffer would still be able to overwrite the stuff up here, though, and we're going to see why that's still going to be a problem. But yes, if the password was initialized after the buffer, then this wouldn't have worked. So that's good. It's good that you spotted that. That means you're catching on. I'm happy to see that. So again, our Mimi hacker man, congratulations, you got the flag. So here is a program called Overflow 2. This one is a pretty good jump in difficulty. So this program is pretty straightforward. Again, here's the main function. You're going to see this thing here, set vbuff. Basically, just don't worry about this. This is something that we have to do to make this work when you connect to it on the internet. Then it's going to print out enter input. It then runsfflush. That's going to make sure that this print statement runs. Sometimes that doesn't happen when you connect to it online, so I have to put that in. Then it's going to call this totally safe function. Totally safe has a character buffer of size 40, and then it calls gets into the buffer. When that's done, it goes back to main, and then the program quits. The flag is printed out by this function up here called Printme. The trick that you want is to somehow get the Printme function to run. So I'm going to give you guys, let's say I'm going to give you 5 minutes and check in with you in 5 minutes to see how it's going. Like I said, don't be surprised if you get frustrated by this one and can't do it. There is a sort of jump here. I think you can probably make the jump conceptually, but figuring out how to actually do it in 5 minutes might be pretty challenging. But give it a shot and see if you can figure it out. I'll come back with some hints in, let's say, about 5 minutes starting now. And again, just toss questions in the chat if you have questions. All right, coming back in. Do people want more time? Should we get going through this? Anyone manage to get it? Got one response. Someone said they don't know how to do it. That's perfectly fair. Do you have an idea for how to do it? Might be the better question, at least. Because what we're going to do after this is show a bunch of ways of how to do this. Okay. Give you just another minute, see if anyone else. Right. Looks like people have a fairly good idea. Some people have an idea. Dante, I think, has the right idea. Presumably, we want to overwrite the return pointer. Here's the answer. And yes, a few people have got it. I think you probably want to overflow the buffer and rewrite the return address of totally safe to Printme. Okay, so we're going to take a look at this, but first, let me ask you a question. Is this a string or a memory address? Toss it in chat. I apologize for the big long silences. It takes a long time for the stream to get to you, and then for you to type your response, and then the response to get back to me. Answers include both, and yes. Good. That's the right answer. Everyone's got the right answer. We don't know. This could be either. Remember, the computer only knows what this is based on the context it's reading it in the same way that if I said that's sick, that could mean that's cool or that's awesome, and that could also mean that's disgusting. You need context for these things. So that could be a string, or it could be a memory address. And understanding that is important for understanding how we get to Printme. This is the hint, but I'm going to go ahead. We're just going to go ahead and do this. The hint is figure out how to get the memory address of Printme, but I think people got the right idea of how to do this. So yeah, what we ideally want is to figure out how to get the memory address of Printme. So here's the program down here. I've taken out all the extra stuff. So we just have a basic little program. So we start out in main. Again, here's our return address from main. So this is, when I say the return address from main, this goes to whatever started the main program or whatever started this program in the first place. So yeah, main then calls totally safe. Totally safe goes here. It gets the return address to main, and the frame pointer then fills in the buffer. That's all space for the buffer where the characters are going to get written. Then it calls the gets function. So you might have seen me working in the background. I screamed at the program to see if I could get a seg fault. I could. That was a good sign. That means that there's some bad memory manipulation going on in here. So we write into the buffer. We write it full of A's, capital A's, which I believe are 4-1. That was what I was confused about earlier. And usually we would just keep writing. I've shown you how to brute force this. We overwrite the frame pointer, And then the trick here is we don't want to just write A's over the return address and send the computer to a place where we're going to get a seg fault. We can write something into the address space that's going to be the address of the printme function. And we could write it in characters if the address of printme translated into characters easily, but it probably doesn't. But if it was, if the return address for printme could be translated into just characters on our keyboard, we could just type characters in and write over that return address and then jump there. As it is, we need to write probably some bytes, not just characters, but bytes, specific bytes in there, and the bytes that are the return address for printme. So we need to do a few things then. We need to figure out where and how do we get the address for printme, and then how do we feed that into our program to destroy it. So yeah, if we get the return address for printme, then we can jump into that printme function. And this is a really common sort of beginner binary exploitation problem that you're going to see in capture the flag competitions. The ability to jump to a different function is usually one of the earlier sorts of problems that you encounter. This is one that Alex, the club president, and I solved right before we started the club. We were doing a CTF. We did a challenge like this. We were up till 3 a.m. in the computer science labs. We had solved it, I think, hours before, but we couldn't get it to accept the answer because we were typing it in the wrong way. But at 3 a.m. we got it, and we were overjoyed, and we just thought we were the greatest things ever. So yeah, let's look at how to find the address for printme and then how to feed it into the program. So the first thing that we're going to need to do is we're going to need to figure out where the return address is in the memory. So we can look at what's in here. We know that there's a buffer. It holds 40 characters, but we also know that there's the frame pointer and then the return address. Sometimes also the program can put other stuff in there. There might be a few bytes off in one direction or the other. There might be something else in there. If there's arguments that are provided, those get put in between the buffer and the return address. So it'd be nice if we could figure out where that return address is, and thankfully we can. And the way that we can, let's make this bigger. The way that we can is by using Pwn tools. Pwn tools has a function called cyclic, and that is going to help us find that return address. So I am going to start up Python 3. So here we go. Python 3 is running. I'm assuming you guys can see this. The first thing that we're going to do is import the Pwn tools library. This is really common in CTF binary exploits. So from Pwn import star. There, now we have access to the library. Now we're going to call the cyclic function. So I type cyclic, and then I tell it how many, it's going to print out some characters for us to try to find how big the space is before the return address. So I'm going to say cyclic, I want 100 characters. It then spits this thing out to us. And this is what we want. So this is called I've tried to get the pronunciation of this right, a de Bruijn sequence. It is a pattern. So it's 4 A's and then a B. And then, it's AAA, then ABA, AAC, AAAD. So it's a certain pattern, and we're going to feed this into our program, and we're going to see where it tells us the problem is. It's going to tell us that it tried to jump to an address. The address is going to be probably one of these is going to be someplace in this sequence of characters, and that will tell us how big the buffer is before the return address. So I want this cyclic function. I'm going to copy those out. I'm going to go to here, and I'm going to use GDB to run this. Let me make this just a little bit bigger. So I've got all of the files here that I gave you. This was Overflow 2, so I'm going to run GDB and then Overflow 2. So I'm going to tell GDB, the debugger, to run the Overflow 2 program. Gives me a bunch of welcoming information. Then in GDB, I just type run. This is just going to run the binary. So it tells me it's starting the program. It wants the input. I'm going to paste my input in there. There's that sequence of characters that we gave it. Hit enter. The program runs, and then GDB is really kind. It tells us, look, there's a seg fault. I got a seg fault in this program. And then it tells me this. What this is this is the address that it tried to jump to when this totally safe function finished. It tried to jump to this address. This is the return address that we overwrote, and we overwrote it with something in here. We just need to figure out how far into this sequence that was. What do we see? 61, 61, 61, 6E. 6E is probably M or N, I think. So it's probably this part of the character string overwrote the return address. So let's copy this. I'm going to go back to Pwn Tools, and I'm going to use cyclic find. I'm going to paste that in there. So cyclic find is then going to find where in that pattern this is going to show up, how many characters it was, and it tells us 52. So at 52, or character 52, this is where the return address was. This is how we wrote over it. Yeah, Dante's reaction is a good one. This is very helpful. If you guys are in 525, this might help you in your assignments. I'm going to warn you right now, for those of you in 525, I'm going to quit out of this. This is a 32-bit binary that we're doing this on to make this just a little bit easier. It's a little more complicated on 64-bit binaries, but Pwn Tools is going to be your friend if you're in 525. It can help you a lot. So we figured out where the return address is. It seems to be somewhere around 52 bytes or 52 characters in. So if we ran overflow 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's copy that. 2, 3, 4. Let's copy it 5. 5 gives us a seg fault. One, 2, 3, 4. That should be the return address. Yeah, now it's good. So we put 52 in there, and these right here were overwriting the return address. So if I take these 4 off, then these ones over here are going to be overwriting the frame pointer, and then these ones were overwriting the return address. So if I take this and I put 1 more byte in, that's going to start writing over. Yep, this right here is going to write over the return address. Oh, no, it didn't. 2 more? Yeah, 2 more will overwrite. Will start overwriting enough to give me a seg fault for the program to crash. Somebody asked, what was the function in Python you used to pass the address to? Yep, it was cyclic find. So cyclic will give you the pattern, and then cyclic underscore find, and then in brackets what you're looking for there. I'll paste that into the chat for you. That was the command that I used to find out where the return address was. It was at 52. So now I know how far I need to go to get to the return address, and now I just need to overwrite it with the right thing. So how do I find the return address? Well, there's a few different tools that we can use. So let's try GDB first. So I'm going to go GDB overflow 2. We're in GDB now. And GDB is very powerful. If you're in 355, you're probably spending a ton of time using this to try to debug your assignments. If you could really learn to get good at GDB, your assignments would go really quick. And doing a lot of binary exploitation, you get pretty good at GDB. So GDB will tell us about memory addresses in the program. So I'm going to say disassemble Printme. I'm going to tell it, show me the Printme function in assembly. And this is the Printme function written in assembly code. If you did our reverse engineering workshop last week, you did some assembly. This is what it looks like. This thing over here is the address where this is in memory, where the Printme function is in memory. So I could use this. Let's copy that out here. So I'm just going to make a note of this. Printme return address is being held right there. Good. This is the address. These are the bytes that we need to write over top in order to get this. So that's one way to get our return address. This is only possible because I told the program never change this address. One of the security features in programs to prevent us from doing stuff like this is it will change this address every time it runs the program. I told it not to do that to make things easier for us. So let's quit GDB. We've got our memory address. Problem now is how do we print this memory address into the program? There's a few ways we could do it. We could write it manually. The problem is when I type characters into the program, it's taking it in as a string, and I want it to take in bytes. Some of these are not printable characters, like 08 on the Ascii table is not a key on my keyboard that I can press, and that'll turn into 08. So we're going to use Python. So I'm going to type it this way. I'm going to say python-c. So this is basically run a Python command on the command line. And I'm going to import sys. So this used to be, actually, I want to use Python 3. I'll use Python 2. Actually, if I just say, yeah, it doesn't, I don't have Python 2. So I'm going to go Python 3-c and then import sys. And then I am going to say sys.stdout.buffer.write. And then I want my characters, or my bytes. So I'm just going to put this down here. You might not be able to see that, but I'm going to say /x e6 /x, and this is telling it the bytes to write, 91, /x 04 /x 08. You might notice that this is backwards compared to, tell it to write it in bytes. I think that'll work that way. This is backwards compared to what the memory address was. The memory address was 080491E6. The problem is that our computer holds bytes sort of backwards. This is known as big endian and little endian. Sometimes bytes are written from back to front, and sometimes they're written front to back. And this time they're going to be written back to front. And if I did this right, and I'm not confident that I did, yes, it did. This thing right here on my screen, that's the bytes that I just wrote here. It's not a character, so my computer can't print it. But if I take this command and I output it to sample.txt, and then I run xxd sample.txt, there are my bytes right there. Oh, actually, it wrote them in the right order. That's weird. Yeah, so there are my bytes. So I can do better than this. I can put the padding in front of this. So let's take my Python command. And we're also going to write the byte of /x41. Those are going to be our A's times, what was it, 52? So 48, I think, might get us there. Plus, yeah, let's try it. Whoop. And then xxd sample.txt. There we go. Now it's showing us my bytes. So I've got all these 41s. These are going to write into the buffer. They're going to overwrite the frame pointer. And then hopefully we hit the return address with these bytes down here. And I think they'll be written in properly. I might have to reverse that. So let me clear my screen. And if I cat sample.txt, that's what my text looks like. So now I want to cat sample.text into Overflow 2. And it just gives me a seg fault. So something I've done is wrong. And I'll bet you I put my bytes in backwards. So, and I know this is a little bit tedious. It's really impressive if you can get it right. 08, 04, 80491 /E6. Now let's try seg fault again. I'm probably off. Actually, I am off. Why is that 41? Oh no, it's 48. Let's try 52. Still seg fault. Shoot. So as you can see, this is pretty tricky. This is pretty difficult. If only there was an easier way to do this. And there is. That way will work. I'm just going to have to play with the bytes to try to get the address right and to try to get the padding right. But there's a tool we have called Pwn Tools that will make this a lot easier for us. Forgot the X in front of E6. I very much did. Still seg faults. It was a good try. It was a good try. But I have a way that's going to make this much easier. So I am going to call up Vim, and I'm going to write something called exploit.py. This is going to be a Python program. And we are going to use Pwn Tools to do this. And to do it, I am going to take my pre-written script so I have a reference. First, I want to write these things out of this Python program. So I am going to say from pathlib import path. So this is going to let me write stuff to a file. And then I'm going to say the classic from pwn import star. So import the entire library of Pwn Tools. The first thing that we have to do is we have to tell Pwn Tools what program we are trying to exploit. So I'm going to say program equals, and then this is a function called ELF. It'll import our program, and this is Overflow 2. It's in the same directory, so we just call it Overflow 2 like that. So there, it knows what our program is. Then we're going to say padding. These are known as padding bytes. When you're filling the buffer up, everything that you put in to get to that return address or wherever it is you're trying to go is usually just known as padding bytes. So I'm going to say that that's the byte A times 52. So that's just going to be 52 A's. That's what padding is. Then I want to know the address of Printme, and Pwn Tools can get that address on its own. So I can say Printme is equal to yes, I want to pad it. Pack it. So this is a function that's going to pack the address, and then inside of that, I'm going to tell it the address of Printme. So this right here. There. This might look complicated. So what this is doing is, not E, that's supposed to be program. Program.symbols. So what this is doing is saying that program that we loaded before, get the symbols inside of it, so the functions, and find Printme. And this is going to return the address of Printme, this thing. And then P32 is going to pack it. Remember I said that big endian, little endian thing? That's going to pack it in the right way to put it, or to print it out and feed it into our program. So we have Printme, and I'll say just Printme, so we can see what that address looks like. I'm going to say our payload is going to be our padding plus Printme. And this should work. So this thing is going to be bytes. This thing is bytes. It's going to put them all together into this payload. This payload is what we're going to feed into our program to try to not only crash it, but jump. So payload equals, nope, sorry, I've already got that. Now I want to write this out to to a file. So I'm going to say path exploit.txt dot write bytes. So we want to write the bytes payload. So this is going to print out the address for Printme here. So this is another way of figuring out the address for Printme. We could just have pwnTools find it and print it out for us. And then it's going to write our exploit. I'm going to write and quit. And I'm going to say Python 3, and I'm going to run this program, exploit.py, to write our exploit. And it's angry with me, because I've mistyped overflow, which I did earlier tonight. There we go. Okay. So this first thing that prints out, whenever we tell it to open up the program, remember that ELF at the beginning, program equals ELF. This is just showing us information about the program. These things here are all security features for preventing the kind of thing that we're trying to do. And this is the address, the memory address for Printme that we were trying to get before. And if all of this worked, there should be an exploit.text. There, that's our exploit. .txt. So that's our exploit, and it looks really close to what I had before, but let's check. So we're going to cat exploit.text into and run overflow 2. This pipe will send what's ever on this side into the thing on this side, if you're not familiar with how pipes work in programs. Success. It printed out what we wanted. It said enter input, flag file is missing. That's what we wanted. Remember, I'm running this locally. I could now cat this into our netcat command, and where is it? There it is. This right here, I could put it in there, and I should get myself a flag. So let's give it a shot. 138.68.59.14.9974. Hangs, and then I enter, 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 enter. Nope, it's not. And if I remember correctly, it's because we need to add this tack onto the end here, because the program's just hanging, waiting for input. Yeah, there's our flag. I'm going to clear that quickly. I want you guys to try to do that. I am going to copy my program and paste it into the Discord chat, but I'm going to take a few things out that you're going to have to put in, just to make sure that you know what you're doing. But otherwise, we're coming up on the end of our workshop. So I'm just going to keep going for now to finish this off, because we've pretty much hit the end of our time. So yeah, we have filled the buffer, overwrote the frame pointer, changed the return address to that of Printme, and then it printed out our flag and our function. So we looked at how we can find that return address, how we did it in GDB, and then how we can script that answer in pwnTools. And being able to do it in pwnTools makes things so much easier, because it means I'm not manually typing out, and as you saw, forgetting to type a single X in the line and thinking that I've done it wrong. Let me just see. Sorry, I've been ignoring the chat. F is missing in overflow 2. Overflow the time. Okay. Nothing I need to respond to. So quickly, all of this was detailed in a very famous paper called Smashing the Stack. We're 2 hours in now. Smashing the Stack for Fun and Profit, written by someone called Aleph1 in a zine, which is like a magazine, called Frack. It's really famous. You have to read this in Computer Science 525. Maybe you don't have to, but it is really worth a read. It was published in 1996. Great title, written by Aleph1. If you ever do binary exploit problems, you will see all kinds of references to fun and profit and smashing the stack. This is originally known as stack smashing, this attack. It was known before this, but this is the first article that really sort of detailed how to use it and how to use it for evil. We could talk about Heartbleed, but let's say we're out of time. There's an XKCD comic that talks about not a buffer overflow, but a buffer overread. Essentially, you tell a computer, I want to read a word, and then you tell it how many characters is. But if you tell it it's more characters, like if the word is hat, and you tell it it's 500 characters, it would just read 500 characters from memory and spit out stuff in memory like passwords and people's addresses and user credentials and all kinds of bad stuff. And this is called the Heartbleed bug. It terrorized the internet for a short amount of time, and it's a buffer overread. It also, this is the icon, this is the logo for that exploit. It was so bad that it got its own logo. That's how popular it was. So there's a last program. It's called Overflow 3. It is difficult. It combines a number of things that we've seen. It is totally doable by you, though. It combines sort of writing things into the stack and then writing a return address. So here's the main function. It jumps over here. You get to write some things into these variables, and then you have to jump to the win function up here. And using everything we've seen, and I'm going to put my pwntool script into the Discord server. Using everything we've seen, you can 100% get this. If you invest any time into it and you're having a hard time figuring it out, let me know. You can DM me on Discord. I'll help you out with it by all means. This is worth 80 points. That's a lot of points in Discord or with Orchid on our leaderboard. But it's difficult. It's tricky. There's things that I've talked about today that sort of mentioned in passing, and this makes use of them. So there's Overflow 3. And yeah, that's going to be the workshop for tonight. Let me just take a look at the flag. I can see our club chat talking, it looks like, to someone, but I'm not sure who. They might just be posting information in there. If there's any more questions, by all means, toss them in. Yeah, somebody said, I like how we only had 5 minutes to do this. Yeah, that I told you that you're probably not going to get the answer to that one. If you were really clever and looked it up, you might be able to find a website that would have explained that really quickly. But it's not easy to find the exact website. Okay. Yeah, any last questions, by all means, let me know. Otherwise, actually, I did a bad thing. I haven't given you the address for this problem. Let me just toss it into the chat. Just a second for anyone that wants to try. It's not unlike something that you might see in Magpie's CTF happening in February. But it is going to be 8065 is going to be the address. So yes, I did say I will post the pwntool script that I wrote into the Discord. There's actually more stuff that can be done, way more stuff that pwntools can do. It's used for all kinds of way more advanced binary exploit scripting and for finding things. I didn't show it to you here, but it can also be used to... actually, let me just show you my script that I have off on the side while we're here. Here's the script written to connect to the remote problem and solve it. So I wrote it, I just had it write the exploit into a text file. You can actually have it send the information straight to the binary, and it'll spit the answer back out to you. I could also have it just connect to the IP address and the port, and then it'll send all the bytes over the Netcat connection, and it'll get back the flag, and it'll print the flag out for me. So yeah, Pwn Tools is a really, really great tool. They've got great documentation. You'll find a lot of websites that use it all over the place. Let me just put Overflow 3. There's the address for Overflow 3, the Netcat command to connect to the IP address and the port. But I'll toss that script into the Discord server. Otherwise, thanks everyone for coming. If you have any questions, by all means, like I said, send questions in the Discord. I'm always happy to help. I enjoy this stuff. I think it's really fun and interesting. It gets way more complicated. This is really overwhelming, like I said, but you've sat through it and you've exposed yourself to it. Good for you. The trick of this is if you can jump to this win function in here, you could probably jump to anywhere in the computer, and there is so much more complicated stuff that can be done using shellcode, ROP chains, and we have workshops on all of those. We did them last year. They're all saved in our YouTube channel. You can go and watch those if you want to do more stuff with binary exploitation. Otherwise, have a great night, folks. Thanks for staying around. Sorry for going over time, and we'll see you again some point in the future. Good luck with binary exploitation and happy pwning. Have a great night, everyone.